Good evening, everybody. Thank you for joining us this evening for the Department of Environmental Sciences Centennial Panel Discussion, Past, Present, and Future Trends in Environmental Issues. My name is Brian McGonigal. I am the Manager of Alumni and Community Engagement for the School of Environmental and Biological Sciences, as well as the New Jersey Agricultural Experiment Station. We've got a great program tonight. We're really happy to be honoring the department on its 100th anniversary. Just a few things to go over. Microphones will remain muted during the presentation. If you have questions, please submit your questions through the chat function, and then will be answered in order. We're going to have our main Q&A, and then after that, we will get to audience questions. The event is being recorded. It will be posted later for subsequent viewing. And at the end of the event, after you close out, a survey will pop up. If you could just fill out the survey, we'd really appreciate it. It'd be a huge help. Okay. And with that, I will pass it over to Lisa Rodenberg. She is the Associate Chair of the Department of Environmental Sciences. Lisa, take it away.
Hi, everybody. Welcome. Thank you so much for joining us tonight to celebrate the 100th anniversary of this wonderful department. I've been a part of this department for about 20 years, so 1/5 of its existence. And as many of you know, this event has been a long time in the planning. We worked very hard on this event, and we hoped very much that it was going to be in person, but instead we're here virtually, and we hopefully that means that more people will be able to attend, and we'll have an even better event than we ever could have imagined. It's unfortunate that Donna Fennell could not be here tonight. She is our current department chair. Unfortunately, she's dealing with a family emergency, and we wish her and her family well in this difficult time. But I'm here, and I'm very proud to welcome you all. What makes this department so wonderful is the people that I've had the privilege of working with for 20 years, the students, and very much the alumni. The alumni have gone out in the world and made a name for this department. We thank you, and we welcome you all to this wonderful, wonderful event. We want to thank the planning committee. We want to thank the panelists tonight. And without further ado, I'm going to turn this over to Laura Lawson, who is the Dean of the School of Environmental and Biological Sciences here at Rutgers University. You may not recognize that name, some of you are alumni, so you can just think of it as Cook College. Laura Lawson.
Thank you, Lisa. It is the longest name for a school, so Cook College sometimes is a lot easier. So thank you. This is an exciting event. It's my pleasure to welcome you to the Environmental Sciences Centennial event. And as I was thinking about 100 years, I was imagining what the 1920s must have been like for Rutgers, for New Brunswick, for New Jersey. My mind went immediately to like speakeasies and gangsters and that kind of thing. But in the context of environmental sciences, it was also a time of prolific industry along rivers, changes in transportation, the introduction of new sewage systems, all sorts of environmental conditions impacting human health and quality of life. So the founding of the Rutgers Environmental Sciences Program was an act of the New Jersey State Legislature to authorize $10,000. That's not their budget today, but $10,000 per year to enable the Agricultural Experiment Station and the State Department of Health to, quote, conduct an investigation of the biology of sewage disposal, to the end that more effective methods of sewage purification could be discovered, unquote. Ecological studies of the Raritan River by the nascent Department of Environmental Sciences in the 1920s and 1930s are among the first environmental studies of a river in North America and led to the expanded vision of environmental sciences of air, water, and soil at Rutgers and across the nation. The legacy of this act has been the evolution of an amazing group of faculty, staff, students, and alumni who make up the Department of Environmental Sciences. They are now taking on the challenges of 2020 and challenging their students to think about what are going to be the challenges in 2120, 100 years from now. Because in the future, we'll still have to address how our practices affect the environment, which in turn impacts us. So I'm really looking forward to today's talks. I'm going to learn a lot. I really want to see how we can enhance our work together to address many of the challenges that are facing our communities. And so with that, I thank you and I welcome you to tonight's event. I don't know who's next.
Please introduce John.
So I introduced John. So I'm happy to introduce John Reinfelder, who is going to be the host of the panel. Sorry about that, John.
That's fine. Thank you very much. Thank you, Laura. Thank you, Lisa. I'm very honored to introduce our distinguished panelists and moderator tonight. But first, I do have to thank Brian for all of his help organizing our Centennial celebration and for hosting tonight's event. But as advertised, we are commemorating our department's centennial, presenting a wide-ranging discussion of past, present, and future trends in environmental issues. To this end, we've invited 4 Rutgers alumni with broad perspectives on the various environmental problems of today and the role that Rutgers can play in addressing those problems now and in the future. I will now introduce the panelists and the moderator, and as I do, I will ask each to say hello so that you can put a face to the name. Our first panelist in alphabetical order is Tony Broccoli. Tony is Distinguished Professor of Atmospheric Science in the Department of Environmental Sciences at Rutgers University and co-director of the Rutgers Climate Institute. His primary research interest is climate dynamics, especially the simulation of past climates and climate change. He recently served as co-chief editor of the Journal of Climate and was a contributor and reviewer for the Intergovernmental Panel on Climate Change. Before joining the Rutgers faculty, Tony spent 21 years at NOAA's Geophysical Fluid Dynamics Lab in Princeton. Tony is a fellow of the American Meteorological Society and the American Association for the Advancement of Science. He holds a PhD in environmental science and BS and MS degrees in meteorology, all from Rutgers University. Tony, please say hello.
Hi, everyone. It's my pleasure to be here tonight. Thanks for that nice introduction, John.
You're very welcome. Our second panelist is Angela Oberg. Angie is a professor in the Department of Human Ecology at Rutgers. As an urban environmental planner, she examines how to make cities more livable and sustainable, and investigates how the everyday lives of urban residents shape and are shaped by urban ecology and urban metabolism. Before coming to Rutgers, Angie practiced professionally as an environmental planner, working on projects throughout the United States and around the world. She holds a PhD from the Edward J. Blaustein School of Planning and Public Policy at Rutgers and a Master of Landscape Architecture degree from Cal Poly Pomona. Angie, please say hello.
Good evening, everybody, and happy birthday to the department. Really excited to be here.
All right, and our third panelist is Joan Tell. Joan is the Director of Occupational and Environmental Health Sciences at Merck and Company, where she manages an interdisciplinary team of occupational and environmental toxicologists and risk assessors. Current areas of focus include pharmaceuticals in the environment and environmental dimensions of antimicrobial resistance. Prior to joining Merck, Joan worked at Exxon Biomedical Sciences, where she modeled the fate and effects of petroleum products from accidental releases. Joan holds BS, MS, and PhD degrees in environmental science from Rutgers University. Joan, please say hello.
Hi there, everybody. Welcome home, it feels like. It's so great to see everybody and see some familiar names and faces. I'm happy to be here.
Wonderful to have you. Our fourth panelist is David Vicari. David is a professor in the Department of Civil, Environmental, and Ocean Engineering at Stevens Institute of Technology. His research is concerned with the application of numerical models to understand natural variation and human control of stream water quality, biological wastewater treatment, and sustainable resource management. David holds BS, MS, and PhD degrees in environmental science and an MS degree in chemical engineering, all from Rutgers University. So David wins with 4 degrees from Rutgers. David, please say hello.
Hello, John. I'm happy to be here. Finally back after I was here for 15 years to get all those degrees.
I was going to ask you that later, but thank you for letting us know. And thank you for being here, all of you. I'll now introduce our moderator, Kelly Anne Cicalese. Kelly Anne is a broadcast meteorologist at the ABC affiliate WCVB-TV in Boston. Kelly Anne previously worked in the Huntington, Charleston, West Virginia area and at KGWN in Cheyenne, where she was awarded Best Weather Broadcaster by the Wyoming Association of Broadcasters. Originally from New Jersey, Kelly Anne is also a graduate of Rutgers University, where she earned a BS in meteorology. Kelly Anne, please say hello and take it away.
Good evening. Thank you, John. I am so excited to be here for this Centennial event, and I have to say I'm excited for what perhaps the next 100 years will bring for this department. So let's get right into it and get into some questions. I'd like to start with Dr. Broccoli. So Tony, which is weird for me to say because you were my professor, but what have been the biggest changes in meteorology and atmospheric science during the past 100 years?
So I would have to say probably there have been 4 big developments. I'm sure maybe other people would think of additional ones, but for me, the big ones are first, computer technology. Many of the things that we do today as meteorologists in terms of forecasting the weather and also just understanding how the atmosphere works are the result of having computers to both analyze the tremendous number of observations we get of the weather and also to make weather forecasts that extend farther and farther out into the future. Without computer technology, we wouldn't be able to do much of what we do today. The ability to observe the atmosphere via radar and satellites is also another key development over the last 100 years. When you think about, for example, the many hurricanes that we've had this season hitting various parts of the Atlantic basin, we know where those hurricanes are, how strong they are, which way they're moving, in large part because we can observe them by satellite, even when they're far out over the center of the ocean, and by radar as they get closer to the coast. And the aircraft that we send in to penetrate these storms also use radar to sense many of the properties of the storms. The third thing that comes to mind is the application of physics for understanding the climate. It used to be that people who studied the climate thought that it was really just about collecting a lot of observations and compiling those observations and not necessarily trying to link them with fundamental physical principles. But that has been changing drastically, particularly in the latter half of the 20th century, where understanding the physics and dynamics of the climate system really became important. And along with that, the recognition of the importance of climate variability and change. It was originally thought that the climate system was quite static, and that if you knew what it looked like today, that also told you what it looked like in the past or would look like in the future. But over the past century, an understanding developed that the climate can vary and in fact can change as a result of both natural processes and human activities. So I would say computers, remote sensing by radar and satellites, understanding climate as a problem in physics, and recognizing the importance of climate variability and change.
Thank you so much. And on that topic of looking back over the past years, I wanted to switch it over to Dr. Vicari and Dave. I wanted to ask you, what do you see as the most important change in your field since your time as a student at Rutgers?
Well, I would say we've come kind of full circle. When I was an undergraduate, the heritage of the department and what we were still working on were kind of conventional pollutants, sewage, wastewater problems. And that was a response to something that happened, developed really from the beginning of the century, just before the department was founded. The end of the 19th century, the sustainability crisis of the time was sanitation. I mean, cities were kind of hellholes. They were breeding grounds for diseases, and it was a really terrible place to live. And a couple of developments happened around that time that changed everything. One was disinfection of drinking water. which was, I think it was, I'm not certain, it was around 1906, the first city in the world to receive continuous disinfection of its drinking water was Jersey City and Hoboken's water supply. So right here, local to us. A couple of years later, the other end of the pipe saw a great technological advance when around 1914, I think it was, in England, the activated sludge process was invented. And this was a biological process to remove the organic matter basically from domestic sewage. Those twin developments revolutionized things and made our society really possible today. It would have been just a terrible thing. And then just a few years later, 1920, the department was founded. And I think that was the heritage for quite a few decades. But around the time that I was at Rutgers in 1970s, we were pivoting to the new environmental movement, which was focused much more on toxic contaminants, industrial pollutants, and that sort of thing. Joe Hunter was running his analytical laboratory to test drinking water and well water and so on across the state, and discovering problems we didn't know were there because of great new developments in analytical technology. Since then, so then we kind of went away from the conventional pollutants, but since then we've actually returned because now we're starting to get back into sustainability issues because we're finding out that some of those resources, like the water itself and the nutrients that are in our wastewater, are things that are not unlimited. And now we're starting to focus on sustainability. So we're kind of making that circle around.
Thank you so much. And you touched on sustainability, so I actually think this might be a good time for me to pivot over to Dr. Oberg. So in the context of humans and their environment, Angie, how do you define livability, and why is livability critical to urban sustainability?
Well, I'm just going to start by saying I'm thrilled that everyone is talking about sewage. I love talking about sewage. This is my sort of area of study, particularly urban sewage. I was not expecting that to be such a vibrant topic already, just in the first few minutes. So that's very exciting. And tomorrow is World Toilet Day, so perhaps that's appropriate. But I'm going to answer your question, Kelly Anne. So first, I'm going to say that in terms of looking at urban livability, in 2006-2007, we switched globally to having majority urban population. So the world became majority urban just very recently. And the majority of that urbanization is happening in the global south. And so what that means is that we have to understand like northern cities and southern cities, and in order to achieve those global sustainability goals. And when I'm talking about livability, this is a hotly contested concept. Most of the time, people think of livability as being sort of quality of life. And so you'll see these livability indices where I think Vienna always wins. It's the most, quote, livable city. And it just means it's the nicest place to live. When I'm talking about urban livability, I'm talking about the ability to just go about daily life. So, and that's different in different places. So my work is in urban India. So for a lot of folks, this just means having access to basic services like water and sanitation and electrification. In the global north, a lot of what we're seeing is gentrification, or the impact of gentrification. So the ability to live, to have affordable housing. And it's really interesting that Dave just brought up both sewage and Hoboken, New Jersey City, because I am also doing a study of gentrification in Hoboken. Actually, I'm speaking to you from Jersey City right now. And so this idea of livability, if we do not address livability and how it's differentiated across the global north and south, we will not be able to achieve sustainability.
Thank you. And let's bring it over to Dr. Tell. So Joan, what changes have you seen in your field over the last 30 years?
Well, I think it's so funny because it does go back to sewage again, because I think that's going to be all of our favorite topics, right? And for us, it's really the improved analytical measurements and the ability to find more things in lower levels in the environment. So for example, back when I was in school, we were worried about benzene, toluene, xylenes as pollutants in water. Right now, we're talking about nanogram per liter levels of pharmaceuticals or other products, cleaning products that go down the drain and don't get removed as well in wastewater treatment. And do these have impacts on the ecology and things like that? So although the water is much cleaner than it used to be before, there's still lots of room for improvement. And as we detect lower and lower concentrations, we need to raise awareness, and we need to, put that into a risk paradigm, right? So yes, we're finding super low levels of compound X. What does that mean? How can we clean it? Do we need to clean it? And what does that mean for the ecology and for potential people drinking the water, et cetera? So I think that it's pretty interesting how, anytime you think, oh, my day is done, we've cleaned up all of the underground storage tanks in New Jersey or something like that. What else do I have to do? There's always going to be another environmental issue as we learn more, as we are able to detect more, as we are able to see more what's going on as we peel back those layers. So I think that it's job security for us. And it also makes our jobs interesting because it's not the same thing every day. We get to grow with the science.
And I think it's something that along many fields, with environmental science, it's always changing, and it's never boring.
Never boring, never boring. We're always learning something, and it's what we're doing is really important. So it really is fulfilling that way too. So
absolutely. So I did want to bring it back to Dr. Broccoli, Tony. So you mentioned computer technology as one of the biggest changes in meteorology over the last 100 years. And also the understanding of physics and the atmosphere. So I wanted to ask, do you think that for meteorologists in the medium range weather forecasts that have become more popular, do you think the trend will continue where that forecast is going to stretch a little bit farther and farther out and become more mainstream as we move in the years ahead? Also, do you think that the time scale will continue to grow to a point where, we're talking about perhaps 20-day forecasts? And I have to say, as a broadcast meteorologist, this is something that really interests me.
Yeah. Well, first of all, I was trying to think of a way to get back to the sewage theme, since that seems to be so popular.
We're getting out of the sewage.
But I'll try to answer the question more directly. There have been tremendous advances in our ability to forecast further out in time. I was an undergrad studying meteorology in the 1970s, and today's 7-day forecast has comparable skill to what a 3-day forecast was back when I was a student. So we have really been extending our ability to forecast into the future. A lot of that is due to computer power. Computer power is necessary to do that, but it's also come from things that we've learned about the atmosphere. Now, there are fundamental limits to trying to predict what will happen on a given day. This goes back to the work of the late Professor Ed Lorenz of MIT, who talked about the butterfly effect, the idea that even small differences in the starting conditions of a weather forecast will eventually grow so large that the forecast won't have skill anymore. But the limits that Professor Lorenz identified are in the range of 2 to 3 weeks. So we haven't reached those limits yet. I think we will be able to extend day-to-day forecasting farther into the future, not with perfect skill, maybe, but with useful skill. The other area that I think is going to be really important is extending perhaps even beyond that 2 to 3 week period in what meteorologists refer to as sub-seasonal forecasts. Forecasts that maybe go out several weeks or a month in advance. Those forecasts may turn out to be different in their content and style. They may be more about whether or not a particular week is going to be warmer than normal or colder than normal or wetter than normal. But that information can be really useful, particularly in a lot of industries where just being able to recognize that the odds shift a little bit one way or another towards warmer and colder can be really important. Think about providers of natural gas or other utilities. So short answer is yes, I do think we're going to be extending forecasting farther into the future. There might be limits to how much we can do that on a day-to-day basis, but I think extending it into the sub-seasonal area is definitely where we're headed.
And news directors everywhere are rejoicing. Okay, so let's bring it back. Thank you, Tony. Let's go back to Dr. Tell. And I wanted to bring it back to your time as a student and perhaps what lessons you may have learned as your time as a student that you may apply to your job today.
Oh, that's a great question. It's so funny because I saw that Dr. Strom is on, and then even Dr. Vakari was, I think he was my outside committee member for my PhD thesis. So it's nice to see so many familiar faces. And I think it's interesting that the foundations that I learned while I was at Rutgers, I still use today, 30 years after I've graduated. So even just this week, we were talking about sludge retention times for a wastewater treatment project. And then, you know, obviously I'm an aquatic toxicologist, so I harken back to my days with Dr. Keating, Dr. Keating doing daphnids, counting little daphnid pulexes and things like that. And obviously Professor Ukrin was my advisor, and it always goes back to mass balance, right? So those basic fundamentals, you know, stay with you throughout your career. The nuances change and you're going to different things, but those textbooks and those notes that you took back then still hold today. So I think that's pretty remarkable how the fundamentals stay, but then the problems change, right? And then we can always go back to our roots and really, you know, take that to the next level and just but maintain the foundation. So it's pretty interesting, and I'm so happy to see that there were still so many people that I know at Rutgers and still there. So it's really great.
Thank you. Moving to Dr. Vakari, Dave, one of your areas of expertise is the sustainability of global phosphorus resources. How sustainable is the current supply of phosphorus, and what are the environmental issues related to phosphorus use? Oh, excuse me, Dave, I'm sorry, I believe you are muted.
Okay, the phosphorus is it's a nutrient. We need it to grow food. It's a major component of fertilizer. Almost all of it that we mine goes into making fertilizer. Being a mined resource, it is a limited supply. There's only so much in the ground, and we have a fairly good idea of how much is available, and it might be enough for a couple of centuries, maybe. Could run short. Some people think it'll be running short sooner. But the point is, it's an essential resource, and we're using it unsustainably. We're not recycling in any amount. Plus, by wasting it, what happens is most of it runs off from farmland, but also in our sewage. So got to mention sewage again. Goes into our water bodies, and it pollutes the water. And what the problem is, it's fertilizing the water. You get excessive growth of algae. The algae, they have immediate impacts of numerous kinds, but in the long term, they die and settle to the bottom. And this year's algae bloom becomes next year's what we call sediment oxygen demand. The muck at the bottom of the water body consumes oxygen, and that takes years to clear out. So you got the resource issue, you got the environmental issue. Surprisingly, if we could fix one, we'd be fixing the other, and it's kind of a two-edged sword.
We can only hope that over the next 100 years, we are able to maybe make a dent in that issue.
Yes, we are. There are many people trying. There are new technologies, but some of the there's some tough nuts to crack out there.
Sure. Thank you, Doctor. Moving back to Dr. Oberg. So Angie, why is it important for scholars and policymakers to work across global north and the global south to achieve global sustainability goals?
I'm beginning to think that maybe I was in the wrong department with all the sewage talk. So what I will say about this is that, so historically, when we think about the global north and south, we think about the north being the purveyor of information to the south. It was sort of unidirectional. And we've seen through development failures and some successes over the last several decades that it needs to really be bidirectional. And so the reason is because in a lot of the cities, in particular of the global south, southern cities, they're being very innovative in their delivery of services out of necessity because their municipalities are under-resourced. So for example, if you are living in an area of a city that doesn't have electrification or you don't have access to municipal electrification, they're becoming very innovative in figuring out how they're going to get electricity to their house. The same thing for water and the same thing for sewage services. And again, I work in how people deal with that, either anything from open defecation to coming up with decentralized systems, either on site or at the neighborhood level. And so what we are seeing is all of these small neighborhoods coming up with sometimes ad hoc solutions, sometimes very planned and orchestrated solutions. But we have this wealth of data that's being generated in southern cities. And as we look, you guys have all spoken about, have systems that are 100 years old in some places. We're having an opportunity to make better choices. And we can look at the wealth of data that's coming out of the southern cities about how they have tried other things. And we can see what might be applicable to places in the north. And so I think that the acceleration of knowledge transfer across the north-south divide is really critical. And why waste all that information? If people are trying these things, they're doing it for different reasons. So I don't want to at all say that the context is the same. So, you know, a person who's living in a slum in Agra that doesn't have access to a toilet and or to sewage services is not going to be doing it for the same reason that, say, a high-rise building in lower Manhattan has an on-site sewage system. So I'm not saying the context is the same at all. However, I think that we can learn quite a bit about sort of the soft side of this. So not the technology, so it's not different technologies per se, but sort of the soft side of it, the soft skills. So things like governance, how are things being funded? How are things being maintained? What is acceptance? What are the social norms around, say, toileting practices or having to deal with your own sewage to a certain extent? So those are the sorts of lessons that I think we need to be paying more attention to, and having the transfer of knowledge be bidirectional, where we are listening to the global south as well as transferring information to them.
Communication always key in every field. Okay, so let's bring it back to Dr. Tell. Joan, what environmental issues in particular do you see impacting the pharmaceutical industry today that concerns you?
Yeah. I think the issue is actually, you couldn't tell from my camera, but I was really nodding my head a lot, Dr. Oberg, when you were talking about it. And it's one of the issues is antimicrobial resistance, right? So the issues really are related to in the global south, where there isn't access to cleaner water or good sanitation, the use of antibiotics to handle some of these diseases that we get, that we've solved for in the north, is skyrocketing, right? And so so then you have poor sewage treatment plants, and then you have antimicrobial resistant genes in the drinking water, and then it forms a cycle of antimicrobial resistance that's spreading, you know, much higher than in more areas. But the solutions for the north are not going to work for the south. We can't go and build giant POTW structures and drinking water systems, you know, in India. We have to find local solutions so that we can provide good sanitation, so that people can be healthier, so that they don't need to take as many antibiotics. And then, even though that you might seem like a bad thing for a pharmaceutical person, but the issue is we don't want people taking antibiotics if they don't need them, right? So, and that's just spreading antimicrobial resistance around the world. So I think that's really, I think, is one of our public health threats, and especially with COVID now, that's another issue. So what happens, you COVID, you get pneumonia, then you're in the hospital, and then they're just throwing different antibiotics at you, that some may work, some may not work, right? So then that, you know, that's forming another pool of opportunities to become resistant to antibiotics. So I think that's probably one of our biggest issues that we're trying to tackle, and it's something that's you know, going to take a lot of our attention the next dozen years.
Thank you. So Dr. Broccoli, you mentioned climate and climate change, and of course, climate change research has become a really important component of atmospheric science and the program at Rutgers, especially recently. Do you envision new emerging areas of research and new employment opportunities for atmospheric scientists related to climate change?
So I'll take the research side of that question first, and then talk about other employment opportunities. I think on the research side, we have seen a transition from a focus on questions like how much will global temperature change and how rapidly will it change, to thinking about the connection between climate change and extreme weather events. And both Joan and Dave have talked about going back to their roots in one way or another in terms of the field or in terms of what they study. And for me, as someone who studied meteorology as an undergraduate, thinking that maybe I would become a weather forecaster, it's interesting now that when I think about climate change, I'm often thinking about it in terms of its impacts on extreme weather events. So we want to know how climate change will change hurricanes and typhoons and tropical storms around the world. What will it mean for severe thunderstorms, tornadoes, those kind of extreme events, wildfires? And I think that is going to continue to be an area of greater and greater focus, going from the global scale of climate change down to the scale of these actual events that really have huge impacts on people's lives. So on the research side, I think we're going to be seeing a lot more focus on that interface between climate and weather. On the employment side, I think we've already begun to see growth in private sector jobs that are climate related. And that's coming about because many companies are making business decisions all the time that have implications that extend far into the future. And understanding that the climate 20, 30, 40 years from now is not going to be the same as it is today means that these decisions have to be made with an understanding of climate change in mind. In addition, I think there's going to be a market for people who can translate the latest climate science so that it can be used by decision makers in both the private sector and the public sector. People want to understand what climate change means for whatever it is that they're doing. And I think people who are trained in climate science, but who are also good at communicating and good at thinking about the connections to other things that we do, are going to be in great demand over the next several decades.
I have to absolutely agree with you, and to hope that over the next 100 years, we could really make some advancements with that. So with that said, of course, this is the Centennial event. So I thought it would be fun to ask one final question of each of you. Looking ahead to the next 100 years, what advancements do you most hope for in your field? And I will start with Dr. Vakari. Dave, what do you hope for in the next 100 years?
Oh, well, I'm a modeler, right? I make predictions somewhat like Tony does in his field, but I predict things that are physical and biological. Well, one of the last things I like to predict is anything having to do with human nature. But this is what I would hope is that people put a more critical eye on what we're doing and realize how much we're tied together. And I do think to some degree we will be forced to do that, and it'll be hard to ignore the challenges, like unfortunately people do ignore today, and that will come around and really address these problems and consider it not only benefiting us in that direct way, but knowing that the response itself, creates activity and livelihoods and knowledge, and will grow as a society that way. So that's optimism.
Yes, optimism is key. And Dr. Oberg, so what advancements do you hope for in your field over the next 100 years?
So the sort of cop-out answer is livable, sustainable cities, cities that are ecologically viable, but are also livable for everyone. So the real answer is a just city, because many of the things that I've been talking about are the foundation of them is environmental justice. So this idea that some people have access to services and some people don't, that some people can afford to stay and age in place, but others can't. Those are all issues of environmental justice. And the wonky answer is better zoning in the US. For any planners out there, we're not going to get to any of the things that I said until we get some better zoning. And I'd love to have a zoning conversation with someone on the side if they're interested in such things.
Thank you, Angie. Dr. Tell, Joan, what do you hope for?
Well, honestly, I'm going back to my pharmaceutical roots, and it has to do with personalized medicine, where you have targeted therapies to cure cancer or to prevent cancer. And we're making such great strides there, and I think that really will be drive change even from an environmental perspective, right? So if you have such personalized medicine, you don't need as much. You don't have to rely on a bunch of different medicines for your, just picture your grandfather with their pill boxes of the dozen different pills that they have to take every day. Hopefully, we'll be able to be healthier and not have to rely so much on medicines, and we can be much more personalized with the care that we give ourselves and our loved ones.
Thank you. And finally, Tony, what do you hope for in the next 100 years?
Well, I think a lot of what we do in studying the atmosphere, studying weather and climate, is really try to learn more about how our world works, with the ultimate goal of trying to make people's lives better, and in some cases, even saving their lives. We've made great advances in our ability to predict the kinds of dangerous weather events that have the capacity to kill people, flash floods, tornadoes, hurricanes, etc. Continuing to improve our ability to predict these events, and also because it's not just about predicting them, it's also about communicating our predictions effectively. That we'll get better at doing that, I think is what I would hope to see. I think in terms of climate, the best outcome would be for us to develop ways of producing energy that don't put carbon dioxide and other greenhouse gases into the atmosphere, so that our climate doesn't change. As an atmospheric scientist, I'm not sure that I can do much personally to advance that, other than to make it clear that that's an important goal. But our science is increasingly interdisciplinary. And what I look forward to is working with people who are thinking about solutions to the climate problem. And I would hope to see those solutions implemented. My only last comment is to pick up on something that Dave said. There's this quote that has been attributed to, I've seen it attributed to Niels Bohr or Yogi Berra, that prediction is hard, especially about the future. So I suspect that 100 years from now, when we're convening a panel to discuss the 200th anniversary of environmental sciences, there'll be things we're talking about that we really can't anticipate today.
Thank you so much, Dr. Broccoli. And I do believe at this time I'll be sending it over to Brian, who will open up the questions that we received during the chat. I'll be interested to see if any of them are sewage related. Or is it John that I'm sending it to?
Yes, thank you, Kelly Anne. That was wonderful. Thank you, panelists. And we do have questions from the audience, and I'm going to just dive right in here with the first one, which actually harkens back to work done by the very first chair of the Department of Environmental Sciences, Willem Rudolphs, who undertook many, many environmental and ecological studies of the Raritan River, and really used that as a case study to understand the connection between the environment and, at that time, the problem of the day, sewage discharge. But the question is, regards what are the biggest problems facing the health of the Raritan River, and what steps should we take to fix them? And could you ever imagine a future where students regularly swim in the river?
Well, I guess I'll jump in on that. I've seen some studies of the Raritan River, mostly of the upper Raritan, and there are stretches that have severe eutrophication. That's where we have the excessive algae growth, which is linked to this phosphorus pollution that I was describing. And I talked about long-term effects. There's a short-term effect that's really interesting. You get much greater oxygen swings, both high and low, because algae also consume oxygen in the dark. And then by taking out CO2, they shift the pH, which is not very good for fish. I mean, if you took out all the CO2 for typical alkalinity, the pH would go up to 11. So the fish won't like that. So and this comes back to something else that was mentioned. Nothing you've learned is ever wasted. And as an undergraduate student at Rutgers in environmental science, because it was at that time, it was before Cook College, it was the College of Agriculture and Environmental Science. And we were all Aggies, basically. And I had to take a course, whatever my major, in plant science and animal science. Today, I am working with agriculturists to work on this problem of phosphorus runoff from farmland. And the knowledge I gained from my freshman year at Rutgers outside the major is valuable. I'm not so ignorant as I would be otherwise. But yeah, so that's a challenge with the Raritan River. A lot of it goes through farmland, and then gets pumped up to places like Spruce Run Reservoir, where it causes algae growth problems. So the river's problem also becomes a drinking water problem.
It's really it's a watershed problem, I guess would be the way to frame that. But I love the idea of no knowledge is wasted, and I need to remind my students of that a little bit when I'm talking about chemical thermodynamics. But we have a very interesting question, which is hearkening back to that middle period that David was referring to, and I think maybe this is a question Joan can weigh in on, and it's about a perspective on PFAS or other forever chemicals like 1,4-dioxane, things that persist in the environment. And I don't know if Lisa's still around, she could also chime in on this.
Yeah, that's one of the very interesting things, because some of these forever chemicals are critical chemicals, right? So we need them. We can't live without them. And because they're important for medicines, right? So 40% of pharmaceuticals contain fluorinated groups, right? Because they don't break down in the body for that specific reason. But I think there's that balance there, and it's trying to find alternatives and safe alternatives that have been just as tested, right? I think that's one of our problems too, is that we rush to maybe to go somewhere else when we don't have the robust set of data on those chemicals as well. But yes, that's our struggle and that's our future, right? So we've done a great job, our chemical engineers, of inventing these wonderful molecules that have a special fit for purpose, right? But then the unintended consequences, right? So who would have thought, that you would find, DDT in the Arctic, or the PCBs and the DDT of the 60s and the 70s. Now it's the PFAS and the 1,4-dioxane today. So there's always going to be something that we need to manage and that we have to look for. And to me, looking for critical uses and essential uses is going to be important, right? So we have to find out what the most critical uses are for these chemicals. Can we find an alternative for them? Is there something safer? Can we design a drug or use solvents that aren't as dangerous for the environment, and move toward that? So that's happening by regulation. It's also happening by choice by all of the industry, right? So we're trying to always look for safer alternatives. But every factory that makes every factory that makes a medicine is essentially a chemical factory, right? So that's what it is. It's built by chemical engineers, run by chemical engineers. So we're trying to look for safer alternatives all the time, because we can't be making medicines that saves one person's life, right, and putting someone else's life at risk, right?
Yeah, maybe, and then goes into the predictions for the future, trying to understand the persistence of chemicals. Lisa?
Yeah, I was just going to say, you mentioned unintended consequences. I think environmental science is the science of unintended consequences. And I think that maybe one of our goals is to make sure that even though the consequences might be unintended, at least they're not unanticipated. That perhaps we can at least say, yeah, we know it's going to be toxic, and therefore we're going to be very careful about how we use this chemical. But in the past, we didn't even know that. We just were spewing stuff out there and had no idea what it was going to do. And then the other point that I would make, since unfortunately Lily Young is not one of our panelists, I'll have to make this point for her. If there's one thing I've learned as a chemist in this department, it's that microbiology is amazing and microbes can do things that blow my mind. And even though there are forever chemicals, bacteria always seem to find a way to do something about those chemicals. So never underestimate them. They'll always find a way.
That's great.
Thank you. Thank you both. We have two questions on environmental justice. And so this is an area that always causes some distress in folks like myself, physical science trained, but very, very important that we broaden our focus, broaden our field of view to think about the human consequences of everything going on in the environment. And perhaps the way I can combine these questions is how does or how should the issue of environmental justice influence today's environmental science agenda?
I'll jump in here. And so not being an environmental scientist, coming from a planning perspective in the social sciences, I think it's always the questions of why. So why are you asking a particular question? And so there is, coming from looking at research methods through a social science lens, there's always this idea that the question that you ask is subjective. And so there's no objective research agenda. So you can be as far away from social science as you think you are, but the fact that you're posing a question is subjective. And so whenever you get into any subjectivities, all of a sudden there are equity and justice issues. And so as social scientists, we're talking about this all the time, but I would say as physical scientists, just being aware that the question that you're asking is important. So why are you asking it? Who does it impact? Who is going to benefit from those results? Who is being involved in the process of answering those questions? And so that's the way that I think that physical sciences and social sciences can come together, just sort of on a macro level. But on a very specific level, I think that process matters. So that's just on every project that you're working on, research, or even if you're doing some sort of participatory action research. But I think the why is really important. And then also the should. So what should you be doing? And that's an ethics question, which is, I mean, I have a philosophy undergraduate degree, but I try to keep that quiet. So I'm not going to get into the should. But I think from a research perspective, the why is important.
Well said. I struggled a couple years ago with an ethics module in my environmental chemistry course, and it got down to this should and ought to distinction that is difficult. But Joan, did you have something?
Oh no, I was just laughing at one of the chats. Someone was mentioning Dr. Finstein and how happy he would be about the degradation of
oh yes.
So so I'm sorry if I distracted. I apologize.
No, we all fondly remember and miss Dr. Finstein for his quips and insights. There is a question about extreme natural disasters and climate change, and reports informally or formally in the news or the media that there's a connection between climate change and the intensity and frequency of natural disasters. Why is this happening? Are there specific connections that can be made? I throw this out there. Perhaps Tony has something to say on this.
Well, there's certainly some kinds of natural disasters that we anticipate are influenced by climate. For example, when we talk about hurricanes, hurricanes derive their energy from the warmth of ocean waters. And there's a lot of research that has shown that if you make the ocean waters warmer, you will increase the potential strength of hurricanes. Not all hurricanes reach their potential. They're sort of like students in that way. Some of them do, some of them don't. But the ones that reach their potential have the ability to be stronger in a warmer climate. And I think we've already seen some evidence that the strongest storms are getting stronger. Something that's been in the news quite a bit over the past few months have been the wildfires in the Western United States. Obviously, climate change doesn't cause a wildfire in that there has to be a lightning strike or careless discard of smoking materials or somebody who doesn't put their campfire out properly. But climate change can set the stage to make a wildfire more likely. Hotter conditions and drier conditions can make wildfires more likely. And climate change has definitely made summers hotter in places like California, other places out west where the summer is the dry season. So, I think the answer is that there certainly are some natural disasters that are becoming more likely as a result of climate change.
Thank you, Tony. We have just a few minutes left. I feel like it's 7:58. We have a couple questions that have to do with online learning and the opportunity that this COVID situation has presented to us in terms of leading to a different way for education, and perhaps that's a topic I think for another panel. Very interesting, very important, and but that could take another couple hours, I think. But I think your question is very pertinent, and but I'm not sure we know. Actually, things are changing weekly here in terms of our educational delivery. So to be determined, I would say. But I think we're going to wrap it up there, unless there are any final comments from the panel or Kelly Anne. I think we're going to wrap it up there. Thank you all for participating. I want to thank Lisa Rodenberg, Laura Lawson, all the panelists, Kelly Anne Cicalese for moderating. Wonderful discussion, wonderful comments, wonderful questions from the audience. And I want to point our audience to our website, the departmental website, where we've just posted a link where you can get some Centennial swag. We have a new logo for this department Centennial, and you can get shirts and baseball caps and jackets emblazoned with the Centennial logo, and spread the word about environmental sciences at Rutgers. So I'll thank you, and then I think I'll turn it over to Brian for the last outro.
Thank you, John. Thank you so much for your help emceeing the event. I want to thank our committee, the Environmental Sciences Department. You guys did a great job. I think we put together a really nice event. Thank, of course, to Kelly and our panelists, Joan, Dave, Tony, and Angie. And thank you all for joining us from home. We're going to send out a follow-up email to everybody with the video recording. And thank you for helping us honor the 100th anniversary of the Department of Environmental Sciences, and have a great evening.
Thank you all.
Bye.
Thank you.
Thank you so much. It was so much fun.
My pleasure. Good night.
Good night.